Hi everyone, welcome to the first lecture of the second semester of physics. This is a combined lecture for both the calc and the non-calc students, and it's on static equilibrium. So static equilibrium is the physics behind objects that are not moving. Okay, we did a lot of stuff last semester on objects that are moving, and today we're going to talk about, objects that are where the forces and torques acting on them are going to keep the object not moving, and this is known as static equilibrium. It's of particular importance to people who do kinesiology because the human body can be modeled as made up of segments of rigid objects, and you might want to ask the question, what are the forces and torques acting on particular segments of the human body such that you don't fall over? Okay, and it's static, though it isn't like when you're running or anything like that. So like, if you're just sort of standing there stationary, you might ask the question, what are the forces and torques acting at the hip? Things like questions like that. Okay, so we're only going to apply this to rigid objects. Okay, and so I should define what a rigid object is. It's any object which is extended in space and whose shape doesn't change over time. Okay, as it undergoes any kind of dynamics, or in this case statics. All right, so if you take a look at like my remote here, the remote is extended in space. It's got some dimension to it, and it's rigid, meaning that as it moves around or whatever it doesn't change its shape. And you can actually rigorously define what not changing its shape means. It means that if you take any one point and you take another point, the distance between those 2 points doesn't change over time. You can imagine if this thing were floppy, the distance between 2 points might increase or decrease as the object changes shape. Okay, but no, we're just going to allow these things to remain rigid. Okay, now the human body itself is not rigid, but segments of the human body are rigid because our bones are rigid, not totally rigid. We'll talk about a little bit about that later, but my forearm here is pretty rigid. Okay, okay, so it's got a pivot point here, but the segment in here doesn't move, but my wrist does, but the segment in here does not. Okay, so that's what a rigid object is. And static means it's not moving, and not moving means a couple of things, quite a few things actually. It means that its velocity is zero, all right? And if the velocity is zero, then necessarily the acceleration is zero. And that's important because we're actually going to be looking at forces, and you remember Newton's second law relates the acceleration to forces, okay? So because its velocity is zero and stays zero, the acceleration, that is, it's speeding up or slowing down. Remember the difference. Velocity is how fast is it moving. Acceleration is it speeding up or slowing down. Well, if it's not moving and it stays not moving, then its acceleration is zero. Okay. Similarly for its angular velocity. Okay. So not only is it not moving like linearly to the side here like this, okay, but it's also not rotating. All right, so we don't want any kind of rotation. So if there's no angular velocity and it stays stationary, in other words, it continues to not rotate, then its angular acceleration is zero. Okay. Now the reason I made this this distinction with the acceleration is because remember, the acceleration by Newton's second law is what determines the force. And let me remind you now of Newton's second law. It basically says that the net force on an object is equal to ma. Okay. So if a is equal to zero, then the net force has to equal zero. All right, so that's going to be one of the criteria for static equilibrium. The net force has to equal zero. If it didn't, what would happen? If there were a net force, the object would start to accelerate, and then you wouldn't have a situation of statics. Okay, but that's not enough because this is an extended object. Okay, it's not just a point object, it's an extended object. We can talk about it rotating, and it's not rotating and it stays not rotating, and that means that alpha is zero. And then there was that second version of Newton's second law, which is the tau equals I alpha, which basically says that if alpha is zero, if the angular acceleration is zero, then the net torque must be zero. Okay, and so that's yet another criterion that static equilibrium must fulfill in order for it in order for the object not to be unstable, to fall over or whatever, start rotating. Okay, so those are the two criteria. One of them, written here, is that the net force has to be equal to zero, and the other one is that the net torque has to equal zero. Okay, so let's look at each in turn because we really need to understand what a force is and what a torque is. Okay, so remember, force is just a push or a pull, and so we have an object. And I'll do some examples later, and we're going to look at this object and we're going to say, okay, so what's pushing or pulling on this thing? Okay, is it touching something? So there's some kind of a normal force. Okay, is gravity acting on this object? Okay, so we'll look at all the pushes and pulls on that object, and all of those pushes and pulls, they have to add up to 0. If they added up to something, it start to move. You don't have statics. Okay, so because force is a vector, we're going to have to break this up into x and y components, and we'll just do 2D. In reality, you'd have to do x, y, and z components, but we're not going to do that. Once you understand it in 2D, it's good enough. Okay, so that means that the sum of all the forces in the x direction, that is left and right. Okay, we'll take x as left and right. All the forces to the left and to the right, they have to balance. Because if the forces to the left are bigger than the forces to the right, it's going to start to accelerate to the left. Okay, and same thing with the sum of the forces in the y direction. The forces up and down, we'll take y as up and down, those have to balance. So all the forces that are pushing this thing up have to balance against the forces that are pushing it down. If one of them wins, then that's the direction in which it's going to start to move. And again, then you don't have statics. All right, so again, it's the physics of things that don't move, all right, that are static. All right, but that's not enough, because you could have no net force up and no net force down, but you could still get the thing rotating. Okay, and it's probably easier for me to show you later, but just to give you a very quick idea, you could have a force up on this side balancing a force down on that side. So you say 10 newtons up this way and 10 newtons that way. Well, 10 newtons up balances 10 newtons down, but because 10 newtons up is on this side and 10 newtons down is on that side, this thing will start to rotate. And so it's not enough that just the forces up and down balance or left and right balance. You also have to have the torques balance. Okay, and what's a torque? All right, so we did talk about this last semester, but you've probably forgotten. So it's important to get this intuition in your mind. A torque is any force which acts such that it wants to turn something. Okay, I think of it as a twisting force, or a force that kind of wants to turn something. Like whenever you have a screwdriver, you're trying to drive in a screw or unscrew something, you're applying a torque. Okay, because it gets the thing turning. All right, so let me remind you how to calculate torque. All right, so torque is actually given by this formula here. Tau is equal to Rf sine theta, where the quantities R, F, and theta are defined in this diagram here. So let me go through the diagram. First, we have some kind of a bar here like that. Okay, so it could be a bar. I'm thinking like you think of your forearm. This could be like a door looking on, top down or something like that. And it doesn't really matter. The shape doesn't matter, but it's easiest to see this with a bar. So we have this bar here. Okay, and the bar is forced to rotate around a point, and I've drawn that point right there. This is called the axis of rotation. All right, so that's the point around which the object is made to turn. So if I'm going to use my remote here, okay, so see where my fingers are right here, pinching it right there, that's the axis of rotation. So it could rotate around that point. I'm forcing it to be stationary at the axis of rotation here, but it can turn out there. Okay, so that's kind of important. So it's you have to picture this thing as kind of rotating around that. Those are the hinges of the door, if you like. All right, and we're going to apply a force, just one force. Okay, not to complicate things right now. So we have this one force, and there it is. We're applying it right there on the object, and because this is an extended object, where you apply that force makes a difference. Okay, so we're going to apply that force a distance r from the axis of rotations. The axis of rotation is here. The point at which we apply the force is there. The distance between those two is r. Okay. And the force is not being applied perpendicular at any special angle. It's being applied at some arbitrary angle there, theta, like that. Okay. And so if you, I didn't put my r vector right on the diagram, right on the bar, because I didn't want to overly clutter the diagram. But if you were to just start from the axis of rotation and then walk along to where you get to the force, notice that once you get to the force, you got to turn, and that's the angle theta. So the angle theta is the angle between the r vector and the f vector. Okay, and a lot of our problems, the way I'm going to set them up, that angle is going to be 90 degrees. Okay, in general it's not, and you may have to actually use some angle in there. Okay, and you'll see that in one of my problems, but I'm going to try to get it so that you either have an angle of 0, 90 degrees, or 180 degrees. Okay, and so you're going to have to take the sine of that, and you should remember that the sine of 0 degrees is 0, the sine of 180 degrees is 0, and the sine of 90 degrees is 1. Okay, so those are some important angles to remember. Now, just to help you with your intuition here, um, uh, when you're applying this force, you're trying to get this object to turn. Okay, so if you apply the force straight out here like that, okay, imagine that you're grabbing the door right there and you're pulling straight out. Then that angle would be 180 degrees, right? Because it would be all the way around there like that. And sine of 180 degrees is 0. So if you grab the door and you pull straight away from the hinges, like straight out from the hinges, you're not going to be turning that door. You're just pulling away from the hinges. So if the angle is 180 degrees, there's no torque. Similarly, if you're pushing straight in, so imagine now that you're pushing straight in to the middle, then the angle would be 0 degrees, and sine of 0 degrees is 0. Okay, so again, imagine a door, and you grab the door and you push straight in towards the hinges. Again, you're not going to be turning the door because it just doesn't have any of that perpendicular component to the force that's required to get it rotating. Okay, but if you were to push at 90 degrees to the door, okay, so that between the r and the f vector it's 90 degrees, that's when you're going to get the maximal push. And just think about it: when you go to open a door, you grab the doorknob and you push perpendicular to the door. Well, pushing perpendicular to the door, because the r vector is parallel to the door, that means that pushing perpendicular to the door is 90 degrees. Okay, and that's when you get the maximum torque. We do this naturally whenever we open a door. We don't think about this, but that's what this form is encapsulating. Okay, so you get a bigger torque if one, you push perpendicular. Okay, that's when you're going to get the biggest torque. You'll get something at other angles. Okay, you'll get nothing at 180. You'll get nothing at 0. All right, you get the most at 90. All right. The other thing that contributes to the torque is how hard you push. All right, so obviously the harder you push, the more torque you're going to get. And the other one is the bigger R is, the more torque you're going to get. That's why the doorknob is on the other side of the door from the hinges. Because if you try to push at the hinges, if you're pushing right there, then you're not going to get any torque because then R is 0. Okay, so that's torque. Right? Or maybe another example to help you with this, what R is doing is a wrench. Okay, when you've got a wrench and you put a wrench on a nut or something, and you grab it has a handle. The further out you grab the wrench, the easier it is to turn. Okay, if you try to grab it right at the head, it's not going to turn very easily. That's why wrenches will have very large handles, especially some torque wrenches that are used in automotives to remove either put on or remove your manifolds. These are some really big wrenches. You have to have some very long handles because the bigger R is, the more torque you're going to get, even with the same amount of force. Okay. All right. So enough about torque. Let me just remind you what are the criteria for static equilibrium. The net force has to be 0 and the net torque has to be 0. Okay. So the easiest examples in static equilibrium are levers. Okay, and levers it's good to study levers, even though they're very simple, because especially if you're an ESS major, the human body, it's all about levers. Okay, and so what's a lever? Well, it's got 3 parts to it. There's a load. Okay, something that you're trying to lift, okay, or at least in our case, because we're static, we want to just hold it in place. Okay, so there's a load here. There's this triangle here is the fulcrum. Okay, that's the point around which the lever will turn. So this, you can imagine this is like a plank here. Okay, and I've got this box, which is a load on top of the plank, and here's the fulcrum. So the like a seesaw. Okay, it can it can rotate around that fulcrum like that. Okay, and I'm going to apply a force here like this. Whoops, apply a force here like that downwards, and I'm going to apply just enough force such that this load is balanced. Okay, there's an example of a lever. There's actually 3 different types. I'll show you the 3 different types after we're done with this example. So what do I say here? I say a mass of m equals 10 kilograms. That's this mass here, is placed on a lever 2 meters from the fulcrum. So this is the fulcrum here. That triangle is the fulcrum. All right, and the distance from that fulcrum right there to where the load is 2 meters. Okay, so that distance there is 2 meters, and we apply a force Fa, A for applied. Okay, and the distance from that point right there to where we apply the force is 1 meter. Okay, so it's applied 1 meter from the fulcrum, and we assume that the lever is not moving. Okay, and as soon as I say that, that's the criterion for statics. Okay, that tells you that this is a problem in statics. Okay, all right, so there's our situation. What do I ask you to find? I say find the applied force, and with what force does the fulcrum push up on the lever? Okay, obviously the fulcrum here, let me scroll down a bit again. The fulcrum here is pushing up on that lever. Okay, that's what's holding the lever up. Okay, so not only am I pushing down there, or not only am I applying a force, but the fulcrum must be applying a force up. Otherwise, just imagine removing that fulcrum, the whole thing would just flop over, it would just fall. Okay, so I want both the applied force and the fulcrum. All right, so the first thing you're going to do is draw a free body diagram, but it's not like the first set of free body diagrams we did where we just put all the forces in the middle. Here, because this is an extended object, we want to think about where on the object the forces are acting. Okay, so I just redrew the lever here. I got rid of the fulcrum to make life easier. Okay, and here's my applied force here. All right, and the distance from that applied force to the middle here is 1 meter. All right, and here is the load, and I don't know how big FA is. That's one of the questions I want to answer. Okay, here's the load. The load I told you was M is equal to 10 kilograms. So 10 kilograms multiplied by 9.8, but just like last semester, we'll round that off to 10 for the lectures. That's going to give us 100 newtons. Okay, so the force of gravity on that load is going to be 100 newtons. All right, and I didn't say that in this problem, but we're going to assume the bar is massless or of negligible mass. And then there's the fulcrum, and the fulcrum has to be pushing up. Okay, and so the fulcrum is acting right here in the middle, and well, not the middle, but like 1 meter from one of the ends here, and it's acting up, and we don't know how big that is. In fact, that's the second question. How big is FA? All right, and I give you some coordinates here, x and y, but this problem has no x component at all. Okay, it only has forces that are either down or up. All right, so think about the criteria. Let's scroll back so that we could see them again. All right, so the first one is that the net force is equal to 0. But because forces are vectors, it's probably best to think of that as two criteria. One is the sum of all the forces left and right have to balance. That's the fx's have to balance. And all the forces up and down have to balance. Okay, so whenever you hear me say the net force has to be 0, think of it as two things. Think of it as forces to the left and right have to balance, and forces up and down have to balance. Okay, so if you take a look here at the free body diagram, we have no forces to the left and right, so that's out of the picture. But we do have forces up and down, and they have to balance. Now, what I mean by balance is, I wrote it here, I kind of squeezed it in here, forces up equals forces down. In other words, if you add up all the forces up, they had better be the same magnitude as all the forces down, to create that balance so that it doesn't accelerate up or down. Okay, so you just take a look at the diagram, this free body diagram here, and you go, okay, what forces do I have up? Just the up forces. Well, there's only one, the fulcrum force. Okay, there it is. Okay, so the force up, FF. Okay, that's it. That's the sum of all the forces up. And then that's got to balance the sum of all the forces down. And so here we have FA, and we have FG, which was the load, which was 100 newtons. And so all the forces down are FA plus FG. Okay, and we know the value of one of them, which is 100 newtons. And so there's our first equation. Okay, so we got that FF is equal to FA plus 100. Now, you can't solve this, obviously, because it's just one equation with two unknowns. All right, and so you've exhausted all the possibilities with the net forces balancing. Okay, there were no net forces to the left and right, so they automatically balance. There's nothing there. This is the criteria for the forces up and the forces down balancing, but it doesn't specify, like, we don't know how big FA is or FF, because, one could be bigger than the other one, would be smaller proportionally. And so we have to go to the third criterion, or sorry, the second criterion, which is that the net torques is equal to 0. Okay, so and that's the way most of these work out. Okay, I wrote here that the F net equals 0 is not going to be enough to solve this. We're going to have to look at the net torques. Okay, now I usually do forces first and then torques. Some problems, like this one, if you do the the torques first, you actually get further in the problem. It makes the problem easier, but it's not necessary. Once you get to an equation and you say, well, I just can't go any further because I've got two unknowns here. Well, then you have to just move on, and you label the equation, you make use of it later. Okay, you've seen a lot of these kinds of problems even last semester. Okay, so let's look at the torques. Now, at this point, you go back to that torque formula, and I've got it here, RF sine theta, and you say, well, let me start plugging in the numbers, except that you realize that there's a kind of an ambiguity at this point. See that R, it's the distance from the axis of rotation to wherever the force is acting. But the axis of rotation is that axis around which the object is rotating, except that we're in a static situation. And so there is no rotation. And so you say, well, where is this axis? Because it's not rotating. You might say, well, is it at the fulcrum? Because in principle, it might rotate around the fulcrum. If I allowed it, if I, have FA and I'm holding it in place and it's not rotating, but maybe I push a little bit more, push a little less, it'll rotate around the fulcrum. And you could definitely put the axis of rotation there. But here's the trick, and this is going to shock you. You could put the axis of rotation anywhere. Okay, as long as you don't move it around in the problem. You just say, for the rest of the problem, this is going to be my axis of rotation. It's going to be here, and it'll work out. And that's because it's not rotating around any point. Okay, so that's a little bit strange. You might go, well, there's this axis of rotation, but it's not rotating. So where is this axis of rotation? You get to choose. And that freedom is actually very important. Because what it'll do is it'll make the problem easier. You'll see that in just a second. All right. In fact, I'm going to do this. I'm going to solve this problem twice. I'm going to do it with the axis of rotation at one point, and then the axis of rotation at another point, and show you that it gives you the exact same answers. Okay. So, all right. So let's get back to it. We have to balance the torques, and to balance the torques, we have to calculate the torques using R of sine theta, and to get that R, we have to know what the axis of rotation, where the axis of rotation is. And so I say, let's choose the axis of rotation at the fulcrum. That's a free choice because you can choose it anywhere. Obviously, choose it in a place that's going to make the problem easier, and you'll see how that works as we do more problems. Okay, so all right, so let's do the torque due to the applied force. Remember, every force has a potential torque associated with it. There were three forces: the applied force Fa, the fulcrum force Ff, and then the load Fg. Each one of those has a torque associated with it. Okay, and so here's the torque due to the applied force, and you say, okay, let's calculate R of sine theta. And R, you say, well, how far is the applied force from the axis of rotation? So let's just scroll back up to the diagram for a second here. Basically, that R is, what's the distance from the axis of rotation, where that little x is right there, okay, the fulcrum point, okay? How far is it from there to where the force acts? Well, I told you in the problem that it's 1 meter, and you could see that I drew it in here as 1 meter, okay? So that's 1 meter in there. All right, so great. R here is 1 meter. What about F, the force F? Well, we don't know how big that force is. We're trying to solve for that. But we have a name for it, Fa. And so I'm going to put for F there, I'm going to call it Fa, because it's not any old force. It's the applied force in this particular case, okay? And then there's the angle, and the angle turns out to be 90 degrees. So let's see why. Okay. And again, not to clutter this diagram, but the way you might picture this, say, how do I get that angle? Imagine starting at the axis of rotation, and you're going to walk to where the force acts. So you're going to start here at the axis, and you're going to walk to where the force acts, and then you want to walk in the direction of the force. Notice that you have to turn 90 degrees to walk in the direction of the force. So let me just do that again with the cursor. So you move along here, and then you turn 90 degrees, and you move along there. Okay, so I think you could see that R and F are at 90 degrees to one another. In fact, in this problem, they're all 90 degrees. Okay, so there you go. And so the angle here, theta, is going to be 90 degrees. And then when I multiply this all out, I'm going to get Fa, which is an unknown, multiplied by 1 meter. Okay, and I left the 1 meter there just to carry the units. Maybe I should just remind you what the units are for torque. Sine theta doesn't have units. Force is Newton, and the distance is meter, so a torque is a Newton meter. Okay, and over here you see that I wrote counterclockwise, and that's going to become important because with the forces it's up and down and left and right, but with the torques it's clockwise. Torques have to balance the counterclockwise torques. Okay, and why is that? Well, because some torques are going to want to turn this thing counterclockwise, and some of them are going to want to turn it clockwise, and they have to balance against one another. Okay, because if the clockwise torques win, well, then over the counterclockwise, then that's the direction in which it's going to start turning, and then you don't have static equilibrium. So it's the same logic as up, up and down balancing, left and right forces balancing, but now it's clockwise, counterclockwise forces balancing. Okay, so you say, well, how did you determine that this one was counterclockwise? That's what I found, with students. They find this a little bit hard. Okay, so let me talk you through it and maybe demonstrate with my remote here. So imagine that this thing were allowed to turn around the axis, like you pin it there. Okay, and it's allowed to turn. And then imagine there are no other forces acting except for Fa. All right, so you picture this here, this bar. Picture it being pinned so that it can turn around there. So, this side can go up or down, and that side can go, down or up like that. Okay, so it can turn around that point. So if I were to demonstrate this with my remote, see my finger's pinching it here in the middle. That's where the fulcrum is, and it can turn either this way or that way around the fulcrum. Okay, around the axis. Okay, which is at the fulcrum. But okay, so picture what this one's going to do. FF is gone and FG is gone. You're just going to look at this one. So if I'm pushing down on this side, okay, and nothing else is pushing on this, I'm pushing down, then this side's going to go down. Well, this side's going to go down, this side is going to go up, and this thing is going to start to turn like that. Okay? And you say to yourself, is that clockwise or counterclockwise? That's counterclockwise. It's counterclockwise. Okay? So I mean, I guess I could try to demonstrate this with this here like that. And let's see, is this the, yeah, okay. So imagine that I'm pushing down like that. See, which way is it turning? All right, it's going to turn, the side's going to go up here like that, and the side's going to go down, and that's counterclockwise. Okay, so over here, I labeled the direction of the force, the sense of the force, the sense of the torque as counterclockwise. Okay, so there's a counterclockwise torque. All right, now this will get a little easier as we go on because you're going to see a lot of these. All right, the sense, whether it's clockwise or counterclockwise. Now, what about the torque due to the fulcrum? That one is easy, and that's because R is equal to 0. Okay, the fulcrum acts exactly at the axis. And so if R is equal to 0, the distance from the axis to where the force acts is 0. It's acting right at the axis. And a force that acts at the axis can't turn the object. Okay? And so that torque is 0. And that gives you a clue as to how to choose where you're going to put this axis. Because you can put it anywhere. Why not put it at the point where it's causing you the most problems? Like where you have a lot of forces, unknown forces. The point that has most unknown forces, that's where you put that axis, because then the torques due to all those unknown forces is 0. Okay, even though you don't know the forces, you do know the torque due to those forces, which is going to be 0, and that makes life a lot easier. So the torque due to the fulcrum with this choice is going to be 0 Newton meters. Okay, and so there's another one, and then we have to do the third torque, which is the torque due to that load. Okay, and R of sine theta there. Now that force Fg is 2 meters from the axis. Okay, and the force, we do know that how big that force is. That force is 100 newtons, and the angle is again 90 degrees. Okay, and it's clockwise. Let's look at the diagram so we can see why. Okay, so the first thing was R. Well, from the axis here to where the force acts, 2 meters. I told you that in the problem. Okay, so that's 2 meters in there. Okay. The second thing is I told you how much mass there is, so you know how much weight it has. It's 100 newtons. So there's your F. So you know R is 2 meters. You know F is 100 newtons. What's the angle? Well, again, just imagine this little walking thing. So you just start here at the axis and you walk out to where the force is, and then how far do you have to do, or how much do you have to turn? 90 degrees. Okay, so you can see here that that's a 90-degree turn like that. Okay, and so that angle is 90 degrees. All right, so the theta is 90 degrees. So we have r is equal to 2, f is equal to 100, theta is equal to 90 degrees. What about the sense? Is this going to be a clockwise or a counterclockwise torque? And again, just imagine that torque is gone, that force is gone, that force is gone. It's allowed to pivot around this point here, okay? And this force is going to push down. So I'm going to try to demonstrate this like this, okay? And over here, this is the force it's going to push down. It's going to push down, and this thing is going to turn like this. Like that. Okay, it's going to turn. So this side's going to go down, that side's going to go up because it's pinned there. So that's the point that's not going to move. If this side goes down, then that side has to go up. It's a rigid object. Okay, so this is going to go down, and if I kept pushing, okay, if I kept pushing, then it's going to rotate like that around the axis, and that is clockwise. Okay, and it has to be clockwise, okay, because this one's counterclockwise. In these problems, even if you're having a little bit of difficulties with the clockwise and counterclockwise, you should at least intuitively see that this force here wants to turn it one way, and that force there wants to turn it the other way, okay, because they're on opposite sides of the fulcrum. Okay, so one of them wants to turn it this way, the other one wants to turn it the other way. Okay, that way and then that way. Okay, and those two have to balance because that's the whole point, that the torques have to balance in order to get statics. Okay, so let's take a look here at what I did. So there's the torque due to the load, and R is 2 meters, F is 100 newtons, theta is 90 degrees, and we determined that it was a clockwise, and so that's going to be 200 newton meters. Okay, great. So now what? The clockwise torques have to equal the counterclockwise torques. Why? Because the net torque has to equal 0. Okay, so I didn't want to use a bunch of signs like positive and negative signs. You could say, look, the counterclockwise are like the positive torques, and the counterclockwise are positive, the clockwise are negative, and so the negatives and the positives will all add up. But I think intuitively it's just easier to say, well, all my torques in one sense have to balance all the torques in the other sense. So my clockwise torque, I only have one, 200 newton meters, and my counterclockwise torque, I only have one, Fa times 1 meter, like that. And you'll notice the meters cancel out. So I kept it there just for that 1 meter, I kept it there just for the units. You'll notice that the meters cancel out, and I just get that Fa is equal to 200 newtons. Okay, that answers part A. Right, that answers the question, how much force do I have to apply? Okay, so the load was 100 newtons, but I have to apply 200 newtons in order for this to stay in equilibrium, okay, static equilibrium. Now, I also asked for the force that the fulcrum has to apply, okay, so the fulcrum force. And for that, we had this other equation here, equation number 1. Let me remind you, when we looked at the balancing of the forces up and down, we had that FF is going to equal Fa plus 100. We know Fa now, so we can calculate FF, okay? And so just substituting back into equation 1 here, okay? For part B, we're asked for FF, just substitute Fa is equal to 200 into equation 1. There's equation 1 rewritten. We know that Fa is 200. 200 plus 100 is 300. So the fulcrum has to apply 300 newtons upwards, okay? All right. Now, that ends the problem, but I just wanted to show you that you really could choose the axis anywhere. I don't recommend that you do this like for all the problems, but I think for this very simple problem, it's nice to show you that had you chosen the axis of rotation at some other point, it would still work out. Okay, you could go crazy. You could choose it like even outside of the plane of the lever. Okay, you could choose it like, I don't know, someplace crazy like out here or down here. You wouldn't want to do that because then you'd have a whole bunch of sines and cosines and crazy angles like that. It would still work out. That's the funny thing. It would still work out. So for my next example, rather than choosing the fulcrum there, the axis at the fulcrum there, let's choose the axis at Fa. Okay, and so now our torques are all going to be different, but the problem will still work out. You'll still get the same answer that you did, that we just got, okay? And so now imagine that the fulcrum, I keep saying fulcrum, the axis is right there where Fa is, All right. So let's go through these before I look at the formulas. Let's see if we could do this in our head without actually having to, resort to the formulas. So the axis is right there where my cursor is. So what's the torque due to Fa? 0, because Fa now is acting directly at the axis. Okay. What is the torque due to the fulcrum now? Well, now the distance from the axis to the fulcrum is 1 meter. Okay, so r is 1 meter. Ff we don't know. I know we just found it, but like we're pretending that we're doing the problem all over again. Ff we don't know. Okay, and the angle is 90 degrees right there. Okay, see that angle in there is 90 degrees. So if you were to walk, get to the fulcrum and then turn 90 degrees. Okay, and so if you work out the torque due to Ff, it's going to be 1 meter times Ff. Okay. What about the torque due to this 100 newtons out here? All right, so if we start here at the axis and we go all the way to where that force acts, now we've traveled 3 meters. Okay, so there's 3 meters, and then we have to turn 90 degrees, so the angle's still 90 degrees, and the force is 100 newtons. Okay, so it's going to be 3 meters times 100 newtons times sine of 90 degrees, which is 1, so that's going to be 300 newton meters. So this one is 300 newton meters, so this torque must be 300 newton meters. Why? Well, this one wants to turn it, remember the axis is right there, so this one wants to turn it that way around the axis, which is clockwise. This one wants to turn it that way, which is counterclockwise. Okay, and the two have to balance against one another, and so this torque here has to balance that torque there, and this one we just said a minute ago is 300 newton meters. So guess what? That Ff is going to have to be 300 because it's 1 meter there, 300. And so Ff is 300 meters. You get the same answer. Well, okay, so I said that out, verbally because I wanted to, point to the diagram as I did it. Let's actually go through the formulas and you'll see that it works out. Okay, so here I say we could have placed the axis at Fa. Okay, and it still works out. All right. So now the torque due to the applied force with the axis at the applied force is 0. All right, because r is 0. Okay. The torque due to the fulcrum now is going to be r of sine theta. R is 1 meter. F we don't know, and sine of theta is 90 degrees, and that was a counterclockwise torque. Okay, so we get that the torque due to the fulcrum is the force of the fulcrum times 1 meter, and then the torque due to the load, tau g here, is rf sine theta. R is now 3 meters because we're going all the way across the entire bar. Okay, 3 meters. F is 100 newtons because that's the load. Okay, sine of theta is 90 degrees, so sine of theta is 1, and that gives us 300 newton meters, and that one was clockwise. Okay, so the fulcrum was counterclockwise, the load was clockwise. They have to balance. The clockwise torques have to balance the counterclockwise torques. So we have 300 newton meters must equal Ff times 1 meter. The meters cancel out, units work out, and you get that the fulcrum is 300 newtons. Okay, substitute that back into equation 1 and you will find that Fa is equal to 200. Okay, that's the same as we got above. You can take a look later, we found that the applied force was 200 newtons and the fulcrum was 300 newtons. Okay, all right, so you see that you get the same answer. All right, now before we move on to my next problem, so we're done with that one. Before I move on to my next problem, there is 3 different types of levers. We won't go through problems with all of them. They're all pretty simple. Okay, they're all pretty simple, but there are 3 different types of levers, and it's important to know about them because different parts of the body will use different techniques. Mostly it's this type right here, but let's take a look. The first type, I don't remember. I think they're called types A, B, and C. I don't remember, but it doesn't matter. It's not important that you remember the labels. This is the type that we just did. Okay, here the fulcrum is in the middle, the applied force is at one end, and the load is at the other end. So the applied force and the load are on opposite sides to the fulcrum, which is in the middle. Okay, so this is one type of lever, the one that we just did. But there's another possibility, and here it is. Okay, so here you have the fulcrum at one of the endpoints. Okay, you have an applied force up, and the load is down like that. Okay, so obviously the load wants to, remember this thing is forced to pivot around that point there, so the load wants to make this side go down, and so you're going to have to pull up there like that. Okay, this, by the way, is the human arm. All right, so let me see if I can demonstrate this. So over here, I guess it's the mirror image, I apologize, but the fulcrum here is the elbow like that. Right? And the like I might have a load here, like some weight in my hand here like this, and that wants to pull it down, but then something's got to pull it up. Well, I've got muscles in here. The angle is very different for the human arm, obviously, but I've got muscles up here that are going to be pulling up like in a direction like that, and that's how the human arm works. Okay, and that's another type. This one has the fulcrum at one end, the load at the other end, and the applied force in the middle. Okay, and then the third type, as you can imagine, has the load in the middle. So it's like all three possible arrangements. Okay, so here's the fulcrum at one end. The load now is in the middle, and the applied force is at the outer end. Okay, so all three of these, I don't want to do a problem for each one of them. They're all pretty much solved in the same way as above. Okay, and again, you could choose the axis of rotation anywhere you like. All right, most people will choose it at the fulcrum because it tends to be one of the unknowns. All right, okay, so that was a pretty easy problem. Let's move on to we're going to do two more problems in of increasing difficulties. Okay, so here's another one, and here's the diagram, and what are you looking at? So you have a bar here, and this bar has a length of 2 meters, as I say here, length of 2 meters and 5 kilograms. Okay, so in the previous problem, even though I didn't say it, I assumed that the bar that the lever was made out of was of negligible mass. But here, no, the bar has a mass of 5 kilograms. Okay, and so I'm going to have to show you where is the force of gravity acting on this bar. Okay, because we got to draw that free body diagram. Where's the force of gravity acting? Because it acts all along it. Okay, so all right, and then in addition to that, it's holding up a sign of 10 kilograms. So you see this sign here? That's 10 kilograms. And the distance from the wall here, from this wall, to where the sign is attached is 1.5 meters. So the whole bar is 2 meters long, but the distance from the wall to where we attach the sign is only 1.5 meters. Okay? And there it is. And now you can imagine that, unless you had some really, strong hinge here or something, holding that in place, this is going to want to fall down. And so we have a guide wire. Here's the guide wire. It goes up from the end of the bar here. It's up to the wall like that. Okay, so it's attached like that. There's a wire, and I tell you the angle that the wire makes. The wire makes a 30-degree angle in there like that. All right, and so there's the situation, and this is stable. All right, we want to engineer this so that it's stable. All right, so what questions do I want to ask? Well, I want to ask a couple of questions. The first question is, what's the tension in the wire? You can imagine that if I don't put a strong enough wire up there, well, then we're going to be in trouble because this thing is the wire will break and the sign will fall. Okay, but the other one is, what force does the wall exert on the bar? Okay, so what force does the wall exert on the bar? So there's 2 points here, A and B, and I actually have them labeled here. A is like, what are all the forces at point A? Okay, and B is, what are all the forces at point B? Okay, now the force, I said forces at point A. It's actually just one force, but it's up at that 30 degrees. But we're going to break it up, you'll see in the free body diagram, into its X and Y component in just a second. And over here, don't think that the wall is just pushing out. The wall is probably be pushing up too. In fact, it is pushing up. You'll see that as we solve the problem. So, there's going to be a force horizontally, and there's also going to be a force vertically there at the wall. Okay, it's got to exert both components of that force. Okay, so I want to know the tension in the wire there, and I want to know both components of that force there. All right, great. So now what? So we begin by this free body diagram, and you take a look at this free body diagram and you go, whoa, what are we looking at here? It doesn't look anything like what I just drew. Okay, so let's go through it one step at a time. First, what rigid object is it that is in static equilibrium? Because there's a lot of things there. There's the wall, the wire, the sign. Well, really, we're thinking about the sign, or maybe the sign and the bar and the sign, okay? Or maybe just the bar, okay? But it's basically that's the object. We're just going to concentrate here on that bar, okay, remaining static. All right. I know the sign's attached and it's static too, so you could think of maybe at the combined bar object. But I just drew the bar. I just drew the bar. And then you have to ask yourself, what forces are acting on this bar and where? All right. So the first thing is that the bar has a mass of 5 kilograms. So a mass of 5 kilograms is a weight of 50 newtons. All right. And so you say, well, where do I put that 50 newtons? Do I put it over here? Do I put it over there? Because where's gravity acting on the rigid object? All along it, at every point. And so you say, well, how do I do that? Do I put like an infinity of little gravitational forces along here? You could actually. You could do that if you had the calculus to do it, but you don't have to. It turns out, and I won't prove this for you, okay, but it turns out that you could take all those infinity of little tiny minuscule forces and add them all up together, and it's equivalent to one force of 50 newtons acting where? Right at the center of the bar, the center of mass of the bar. So you remember from last semester, there was this center of mass. And what was the center of mass? It was kind of like the weighted average of where the mass is. Okay. For a uniform object or uniform bar, it's in the middle. It's in the geometrical middle of the object. Okay. Now, if it were not uniform, I mean, I wouldn't do this to you, well, I shouldn't say I wouldn't do it to you, but like you don't want to overly complicate these problems, but but if you're looking at the human arm, you might say, the center of mass is probably not in the center because this part of the arm is a little thicker than that part of the arm. So you have to be careful. You have to be careful that the center of mass is not necessarily the geometrical center of the object. But if the object has uniform density, which we're going to assume for this bar, then yeah, the center. So what does that mean? That means that the 50 newtons force acts right at the middle. And where's that middle? Well, if the whole bar is 2 meters long, then the distance from the wall to where the 50 newtons, where you're going to attach the 50 newtons, is 1 meter. Okay, this is right in the middle. All right, so that answers the first problem that you have. Where do you attach the weight, the vector, the force vector that represents the weight of the object? And the answer is at the center of mass. Okay, which in the kinds of problems we're going to be doing is at the geometrical center of the object. Okay, so great. That's the mass of the object. Sorry, the mass of the bar. What about the mass of the sign? Well, I told you that that was attached at 1.5 meters here, and the sign has a mass of 10 kilograms or 100 newtons. Okay, and now because we've got two gravitational forces, I call this one force of gravity B for bar and force of gravity GS, S for sign. Okay, but there's this extra force right here from the sign, and it's 100 newtons. Okay, and I didn't put the distances here because I didn't want to complicate the diagram, but if you're starting from the wall and you go to where the FGB is attached, that's 1 meter, and you go to where FGS is attached, that is 1.5 meters, like that. Okay, great. Let's do the force of the wall. Okay. Now the force that the wall exerts on the bar is going to have two components. It's going to have an x component and a y component. So I call the x component FWX, and I call the y component FWY. Okay, force wall in the y direction, force wall in the x direction. We don't know either of those. Okay, so we can't pretend to know. Okay. What about the wire? Okay, so the wire, you say, well, what did I do here? Because the wire is actually up at 30 degrees like that. But because we have to start balancing forces up and down, left and right, we might as well start breaking these things up into x and y components, because you're going to be doing that in just a minute. And so the wire, the force in the wire, I call it detension, Ft. It's got an x component, Ftx, and it's got a y component, Fty. Okay, so there are the two components of the tension. So the tension Ft, that's like in some direction here, like that, 30 degrees like that. But I broke it up into its x component, Ftx, and Fty, right at the very beginning when I drew the free body diagram. You know you're going to have to do that. Okay, you're going to have to do that because you got to start balancing forces up and down. Now, here's the thing. What about that 30 degrees? Okay, because if you take a look at the diagram here, you can see that that's 30 degrees. Well, even though I broke up the tension into an x and y component, they can't be any arbitrary value. I don't know how big they are, but the ratio of the two has to be such that you get 30 degrees. Okay, and so that's what I did in right here. Okay, to try to explain what I do. So you're going to use this technique in probably quite a few problems like this. So you might as well learn how this technique works. Okay, so we start here. Here's the edge of the bar here, like that. Here's the edge of the bar, and here's the wire, like that, and it's got Ft. It's the tension. Okay, and it's acting at 30 degrees. Well, what did I do? I replaced it with Fty up and Ftx to the left. Okay, but the ratio of the Fty and the Ftx, they have to make a 30-degree angle. So if you take a look here, and what I did here is I made a triangle. So here's Ft, here's the y component of Ft, and here's the x component of Ft, and that angle's 30 degrees in there. Well, what does that tell you? What does this diagram tell you? It tells you that if you take the opposite, which is this side right here of the triangle, that's the same length as that one. So if you take the opposite, which is Fty, and divide it by the adjacent Ftx, opposite over adjacent is the tangent, and that means that Fty divided by Ftx has to be tangent of 30 degrees. Okay, so I can't tell you how big Fty is. I can't tell you how big Ftx is. But the ratio of Fty to Ftx must be such that you get tangent of 30 degrees. Okay, and that's some number. I don't know what it is offhand, but it's some number. Okay, and so this happens a lot in these kinds of problems. I might give you an angle like this. So let's see, when would you use this technique? It's a little bit subtle. Okay, so you've got, I tell you an angle, but I don't tell you the force. So you're going to break up that force. You need to break up that force into x and y components. Okay, because we want to balance them that way. Okay, and you go, well, all right, what do I do? Well, rather than just writing Ft there, how about you just break it up, Fty and Ftx, and then you say, oh, but I know the angle, and so the y component over the x component, Fty divided by Ftx, must be tangent of 30 degrees. Okay, and again, tangent is because it's the opposite over the adjacent. Okay, so this diagram here is meant to be kind of the overlap of these two, so that it shows the relationship between Fty and Ftx and Ft. Okay, Fty and Ftx are just the two sides of a right angle triangle, and Ft is the hypotenuse. Okay, and opposite over adjacent, tangent of 30 degrees is going to be Fty over Ftx. I call that one equation number 1. Okay, so let's go on. All right, so we're good now to start applying those criteria. So remember, the first one is the net force has to equal 0, and we've broken that up into 2. Forces up balances forces down, that's 1, and then forces to the left and balance forces to the right. Okay, so here I started with forces up, balance forces down. Okay, so you just take a look at this diagram, and now you can see the advantage of having broken this one up into x and y components. You say, okay, what are all my forces up? Well, there's only 2. There's Fwy and Fty. Those are my 2 forces up. What do they have to balance? Well, they have to balance all the forces down. They have to balance this 50 newtons plus that 100 newtons. Okay, and so you could write that Fwy plus Fty must equal 50 plus 100. And that's what I wrote right here. Okay, so Fwy up, Fty up must equal 50 down plus 100 down. Well, 50 plus 100 is 150, so you get your first equation. Okay, and you can't go anywhere with that. All right, because again, 2 unknowns. You have to go on. You have to move on, and then you can come back to it. Okay, and I call that one equation number 2. Okay, so equation number 3, I obtained from balancing the forces to the left and the forces to the right. Okay, so let's take a look at the diagram. You say, okay, are there any forces to the left and right? And you go, aha, there is a force to the right, and there is a force to the left, and that's it. Those are the only 2 forces that are either left or right along the x direction. And so Fwx must balance Ftx. Okay, just to remind you why. Imagine that Fwx is bigger. Well, then it would accelerate to the right. Or what if Ftx is bigger? Then it would accelerate to the left. So these 2 have to exactly cancel one another out. They're in opposite directions, so they'll exactly cancel one another out, and the bar won't move either to the left or the right. We have statics. Okay, so Ftx must equal Fwx. Okay, call that equation number 3. All right, and now we're done with the net forces. We have to look at the torques, and the first question when you get to the torques is, where am I going to put my axis of rotation? And the answer is always you can put it anywhere you like, but make life easy for yourself, okay? You know how big that force is, so don't put the axis there. You know how big that force is, so don't put the axis there. You know a little bit more information about this than that, okay? Why? Because you know the ratio between the two. So you want to eliminate as many unknowns as possible. And if you put the axis there, all right, then what's the torque due to FWX? 0. Because R is going to be 0. The force is acting right at the axis, no torque. What about the torque due to FWY? 0. Because, again, the force is acting right at the axis, okay? So when we go to calculate the torques due to these two forces is 0, okay? Great. What about the force, the torque due to this force? Well, that one is easy to calculate. It's just this distance here, which is 1 meter from there to there, multiplied by 50 newtons. And you could see that it's going to be a 90 degree in there. So sine of 90 degrees is 1. That one's easy. What about this one? This one's going to be an R of 1.5 multiplied by 100. And the angle in there is, again, 90 degrees. What about the torque due to FTX? FTX. Well, R is this way, and F is straight back in, so the angle there is 0. All right, so this one has no torque, but that's because it's pointing directly back towards the axis, so that angle in there is 0. Okay, and then what about this one? Well, that one is if you come out here and you turn 90 degrees, so there'll be a torque to FTY. No torque due to FTX, but there is a torque due to FTY, and the angle for FTY is 90 degrees. Okay, so once again, that one, just imagine, like, turn off all the torques, all the forces here. Just imagine FTX. That's the only force acting, and you're pushing straight in towards the hinges of the door. You're not going to turn it. It's the perpendicular component that does the turning. The parallel component doesn't. Okay, so that one has FTX has no torque associated with it. What about counterclockwise and clockwise? So these two have no torques. This one is going to want to turn. And again, imagine that it's going to turn around that point there like that. Okay, so if I grab this like this, okay, so see where my fingers are here? My fingers right here. That's that point right there. Okay, on the diagram, the axis. There's the axis like that. Okay, so if the forces are pushing down like that, they want to turn this thing like this. That is clockwise. So both of those are clockwise, and this one wants to turn it in the other direction. That one is counterclockwise. So we'll have two clockwise torques balancing one counterclockwise torque. Okay, I talked that one out. Let's actually plug it into the equations. All right, so over here, this is the torque at the wall. Both the y and the x component, they're both 0. Okay, and again, because those forces are acting right at the axis. If you're acting at the axis, 0. 0 torque. Okay. What about the torque due to the force of gravity on the bar? All right. Well, it's RF sine theta, and R is 1 meter. Okay, that's the middle of the bar. Remember that. And the force, the bar weighed 50 newtons, so there it is. And the angle there was 90 degrees, and it wanted to turn, that force wants to turn the bar clockwise, so it's a clockwise torque. Okay, and so the torque due to the force of gravity of the bar, 50 Newton meters clockwise. Okay, what about the sine? The torque due to the force of gravity on the sine. R of sine theta again. R is 1.5 meters. Okay, F was 100 newtons, and the angle was 90 degrees. Multiply that all out, it's 150 Newton meters, and it also was clockwise. Okay, so the torque due to the tension in the wire, the x component was 0. Okay, just told you why, because the angle there was 0 degrees, and for the y component, it's 90 degrees. Okay, so R is 2 meters because you're going all the way from the wall, which is where the axis is, all the way to where the wire is attached on the other side of the bar. So that R is 2 meters. The FTY, we don't know. We don't know how big that is, so just leave it as its symbol. Okay, and sine of theta, well, we do know it's 90 degrees, so sine of 90 degrees is 1, and we also know that that force is going to give you a counterclockwise torque. Okay, and now we're going to balance the clockwise and the counterclockwise torques. And what did I do here? Oh, it's just kind of funny here. This over here is just a continuation of that. So FTY is going to, tau TY, the torque due to the tension in the Y direction, is going to equal the force due to the tension in the Y direction multiplied by 2 meters counterclockwise. Okay, so now we're going to balance the counterclockwise torques with the clockwise torques. Okay, the counterclockwise torque, that was just this torque right here. So we just wrote that in there, FTY times 2 meters. And the clockwise torques, there was the two, 50 Newton meters and 150 Newton meters. Okay, and we add those two together. Of course, that's a total of 200 Newton meters clockwise, has to balance this counterclockwise. And dividing through by the 2 meters, okay, notice the meters cancels out and gives you just newtons. That tells you that FTY is 100 newtons. Okay, so that 100 newtons here, let me show you on the diagram. 100 newtons here, okay, is going to balance these two forces here in the other direction. The torques, not the forces. I should be very careful. That's going to be 100 times 2. So that's going to be 200 Newton meters of torque due to that force. And that's going to balance this 200 Newton meters there. Okay. All right. Great. We've got one of the numbers that we need. We have FTY. Okay. Now, when you take a look at the equations above, you'll see that FTY also appears in the equation which balances the forces up and down. That was equation number 2. And so now that we have FTY, we can substitute that into equation number 2. And so equation number 2, I don't think I need to scroll up here. So equation number 2, see that 100 newtons, that was FTY. So it was FWY plus FTY was equal to the 150 newtons down. But we now know that FTY is 100 newtons, and that tells us that FWY is 50 newtons. Okay? And so we've got another number. Okay? Now we've got the up and down forces, all the components. I'll show you that in a diagram in a minute. But now what about the x components? Well, if you take a look at equation number 3, it doesn't really help directly right here. Here's equation number 3, because you don't know either of them. But remember that there's a relationship between FTX and FTY. And that equation was that tangent formula. So as soon as I got FTY, I got FTX, because the two have to be in some fixed ratio to one another. And so FTY was 100 newtons, FTX is unknown, but the ratio of the two has to be tangent of 30. So, just cross multiply and it works out to FTX 173 newtons. Okay, so the tension in that wire has a y component of 100 newtons, but it has an x component of 173 newtons. Well, now I can substitute into equation 3 and get FWX. Okay, because remember, it was FWX was balancing against FTX. Okay, the wall, x component of the wall force, x component of the tangent force, they were balancing. I have the tangent force, the x component of the tangent force, the x component of the wall has to be also 173 newtons. And now we can go back to that free body diagram, which I just redrew here, and we can put in all the numbers. Okay, so what did we find? Well, we found these two we had, 50 newtons and 100 newtons. We had those already. Okay, we found that FTY, y component of the tension, was 100 newtons. Okay, well, as soon as we found that, this one plus FWY had to balance these two. Well, if that's 100, and that's 150, well then that had better be 50 to balance it. Okay, so you see that you got 50 plus 100 up, 150 up, 50 plus 100 down, 150 down. Okay, so you can see that the up forces balance the down forces. Left and right, they do. Okay, 173 to the right balances 173 to the left. Okay, these two, the 100 and 173, they're in a ratio such that they'll create a 30-degree angle in there. Okay, so we determined that. And the only other thing you don't see in this diagram is that the torques actually will work out, but we could do that very quickly. No torques due to these two, put the axis there. No torques due to those two. The torque due to this one is 50 Newton meters, because that's 1. Okay, so that's 50 Newton meters. This distance here was 1.5 times 100, so this one, 100 Newton force, but 150 Newton meter torque. So we got a 50 Newton meter torque here and 150 Newton meter torque here. Again, that's because that distance in there is 1.5 meters. So 1.5 meters times 100 is 150. So we got 50 plus 150 Newton meters for a total of 200 Newton meters clockwise. What about this one has no torque? What about the torque due to that one? Well, this distance here is 2 meters. 2 meters times 100 is 200 Newton meters. 200 Newton meters clockwise, 200 Newton meters counterclockwise balances 200 Newton meters clockwise. Okay, and so the torques work out. Although that one's a little harder to see, and this one might be a little bit confusing. That's a 100 Newton force, but it's 150 Newton meter torque because the R here from the axis to where that force acts is 1.5 meters. R of 1.5 times F of 100 is 150 Newton meters. Okay, so there you go. All the forces are balancing. Forces up, balance, forces down. Forces to the right, balance, forces to the left, and torques will balance. You could, by the way, I won't do this, but you say, well, will the torques balance around any point? Yeah, you could choose the axis there, and the torques will balance. You could choose the axis there, and the torques will balance. You could choose the axis there, and the torques will balance. You could go crazy and choose an axis which is outside of even the plane of this thing, and you'd be doing a lot of trig, but the torques would balance out again. Okay, so that's a nice freedom to have, that you could choose the axis wherever you like, because it allowed us to solve this problem simply by eliminating those two forces from the torque equation. All right. Just to finish off this problem, I thought, well, I've got the components here. You can see here I've got the components. How about we actually combine them together? Because we did this last semester, but it's probably important that I remind you for this semester. Like here you have X and Y component. What is the tension itself? Because I didn't ask for the X and Y component. I asked for the tension. Okay, so how do you combine the X and Y component? And the answer is Pythagorean Theorem. So in order to get the actual tension, you do the x component squared plus the y component squared, and then take the square root of that, and that's 200 newtons. Okay, so the actual tension in the wire is 200 newtons. The components are 100 newtons up and 173 newtons to the left, but combining them into like the magnitude, and that's going to give you 200 newtons. Okay, same thing for the at the wall. You have the y component was 50 and the x component was 173. You square the two components, add them together, take the square root, and that gives you 180 newtons. Okay, so the wall is actually exerting 180 newtons of force. Okay, 180 newtons of force. And then even though I didn't ask this above, I'll ask it now. What angle does that 180 Newton force make? Well, you've got the x component, you've got the y component. We know that the magnitude is 180, but what's the x and y? Well, above we found that the y component was 50. We found that the x component was 173. And so the angle that it has to make is the inverse tangent of the y over the x component, 16 degrees. Okay, so the wall is not pushing straight out on the bar is pushing up a little bit. Okay, because not only does it have to push the bar out, but it also has to keep that side from slipping down. So if you go back to the original diagram here, you might say, well, why is it up at 16 degrees? Okay, it's kind of up like that. Okay, well, that's because if this were like totally smooth here, this part of the bar would just slip out. Okay, so the wall must be pushing up just a little bit to keep it in place. Okay, that's kind of subtle. All right, if you're less experienced at this, you might have said, oh, well, the wall is just pushing straight out, kind of like a normal force. No. The wall is pushing out, but it's also pushing up a little bit to keep that point B from slipping down. Okay, so don't make that kind of assumption. There's both components there. All right. That ends this problem, and let's do one more problem. This is a classic problem for static equilibrium. It's the ladder sitting up against the wall. Okay, and so what do I have here? I have the ground, and here's a smooth wall. You'll see why it's smooth in just a second. It's a smooth wall, and The ladder, I've put this ladder at a very steep angle. Okay, so you wouldn't want to walk on a ladder that's like put this way. The base of the ladder here is 4 meters from the wall, and the top of the ladder here, this tip of the ladder here, is 3 meters. Okay, so it's not sitting the way you usually put a ladder. Usually put a ladder, at quite a steep angle. This one is kind of at a very low angle, so it's not meant for you to walk on. Okay, just thought I'd mention it because if you're trying to picture this intuitively, you would go, geez, am I picturing it right? Yeah, you are. Okay, this is not like how you would normally put a ladder. Normally you put a ladder up like that. This one's at quite a steep angle. Okay, sorry, quite a flat angle. All right, so a ladder of mass 20 kilograms is placed against the smooth wall as shown. Okay, because the wall is smooth, there's no friction here. Okay, it only exerts a normal force. Okay, that's why it's smooth. So if this were not smooth, you might say, hey, is there going to be a force up or down here? Okay, there's definitely a force out because like a normal force. Okay, but is there going to be some force up or down, kind of a friction along the wall? And I said, no, it's smooth. So there's going to be the force here at the wall is going to be straight out, purely a normal force. Okay, so I did make that very clear in here. Because the wall is smooth, in other words, there's no friction, it can only exert a normal force. All right. All right, but the ground is not smooth. Okay, so it exerts both a normal force and a frictional force. Okay, and you'll see that in my diagram in a minute. If it didn't, well, then the ladder would just slip down. Okay, and then we wouldn't have statics. Okay, so it exerts both a normal and a frictional force. And the first question is, what is the force of the ground on the ladder? Okay, and the second one is, what is the force of the wall on the ladder? All right, so free body diagram. Here we go. What's going on here? Well, let's start off with gravity. Gravity, the ladder has a mass of 20 kilograms, so it's going to have a weight of 200 newtons. Okay, and you attach that vector right at the center of the ladder. There it is, at the center of the ladder. And which way is it acting? Straight down. All right, straight down like that. All right, 200 newtons, acting at the middle, straight down. All right, now what? Well, the ladder's up against the wall. I didn't draw the wall here, but there's a wall there. Okay, and the wall can only exert a normal force, so there it is. And I called it FW for F wall, but it is a normal force. Okay, it's a touching force. Okay, there's no gravity, so you're not going to draw a vector up like that or a vector down, which would be the friction due to the gravity of a friction due to the wall on the ladder. But down here at the ground, there is friction, okay? And so the ground is not only going to push up, and I called it F capital G, G here for ground, not gravity, little g for gravity, capital G for gravity, F for ground. So FGY, up, okay? And there is some friction, and it's FGX in like that, okay? And it's in this direction. I think you can imagine that the ladder would slip out. The ladder would slip this way if there were no friction. So the friction is pulling it back in the opposite direction. All right, so there you go. There's our free body diagram. All right, and now what? Well, let's go through all the criteria. Forces up, balance, forces down. Forces to the left, balance, forces to the right. Torques will balance. Okay, so let's do forces up and down first. And if you take a look at the diagram, forces up, there's only one force up, F capital G Y. That's the force of the ground up, force of the ground in the y direction. Okay, and that's got to balance the force of gravity down, and we know what that number is, 200 newtons. Okay, there you go. So the ground is pushing up with 200 newtons because gravity is pulling down with 200 newtons. Makes sense. Okay, so there you go. There's equation number one, and we actually have one of the unknowns. Okay, F capital G Y. All right, now forces to the left and right. I probably shouldn't have scrolled down. Forces left and right. That's pretty easy. There's just the ground here to the right and the wall to the left. Okay, so F capital GX must balance FW. All right, and there's another equation. We'll call that equation number two. And we can't get any further than that. All right, we can't go any further. All right, now for the third one, the torques, we're going to need some angles, and we also need to make a choice. Okay, so there's a lot of different ways to approach this, and this is the hardest part of the problem. I think you would admit that balancing the forces was pretty easy. This force here up balances this force here down, and this force here to the right balances that force there to the left. But then you say to yourself, okay, the torques, and where do I choose my axis? I've done this different way with students, and most students find it easiest to choose the axis right there because it just eliminates one unknown, that FGX. Okay, I have chosen it, believe it or not, right at the base of the wall, like right there. Okay, that's another possibility for these problems. And it tends to confuse students because you have to use similar triangles, but you have to use similar triangles any which way. But for this particular approach, I think it's probably easiest for these types of problems, ladder problems, to just choose the axis right there at the point where the ladder touches the ground. Okay, so there's our axis. All right, that'll eliminate the torque due to these ones, but then you have the torque due to that one and the torque due to that one. The distances are easy because the entire length is 5 meters. And you say, wait, I didn't give you that. But you know that it's 5 meters, and here's why. If you take a look, this is forming a triangle. 4, 3, and that must be 5. This is the famous 3, 4, 5 triangle. If you do Pythagorean Theorem, the ladder is the hypotenuse, okay? You would do 4 squared plus 3 squared, okay? And then you take the square root of that. And 4 squared is 16, 3 squared is 9, 16 plus 9 is 25. Square root of 25, 5. Okay, so the length of the ladder is 5. So I'll do this, I'll show you the math in a minute, but the distance from this point here to that point there, in other words, the full length of the ladder is 5 meters, and the distance from the axis to where gravity axis is going to be 2.5 meters. Why? Because it's half of the 5 meters. Okay, so the R's are easy. The forces, you know one of them, the other one you don't know. But what are the angles? That's where this one gets difficult. This problem gets difficult. What's that angle in there? Because you see now the R vector is going to come up along here. You're going to get to there. And you're not turning at 90 degrees, which would be this way. You are turning at some angle there like that. And we don't know that angle. And then, even worse, you're going to come up here, and then you're going to turn at that angle there. So what's that angle in there? Right in there. So we're going to need that angle in there and that angle in there. Okay, so we have to do a little bit of geometry. There's no way in this problem to avoid the geometry that I'm going to show you. Okay, there's no way to avoid it. So here it is. To get the torques, we're going to need some angles. And here is a 3, 4, 5 right angle triangle. Okay, and this angle here, sorry, that the number's a little small there, but that angle right in there between the 4 and the 5 side, okay, that's 36.9 degrees, and the angle between the 3 and the 5 side there is going to be 53.1. Okay, so first thing, why is that 5? Well, I showed you here 3 squared plus 4 squared. Take the square root of that, it's going to be 5. So this is a 3, 4, 5. And then for this angle here, just do the opposite, which is 3, divided by the adjacent, which is 4, and then take the inverse tangent of it, right? Because the tangent of theta is going to be the opposite divided by the adjacent. So the inverse tangent of the opposite over the adjacent is the angle. Okay, so the inverse tangent of 3 divided by 4, you do this on your calculator, you get 36.9. So if this angle right in here is 36.9, that angle must be 90 minus 36.9. Why? Well, because the sum of all three angles must be 180 degrees. One of them is 90, right? Because it's a right angle triangle. So these two angles in here have to add up to 90 degrees. So if one of them is 36.9, the other one has to be 53.1. Okay, so I hope that geometry wasn't too much, and it does come up in these ladder problems, so just be aware of that. But why did you need this? Why did you need this? Well, because if you take a look, this 5, 3, 4, that's going to be similar to all our triangles here. So let's go back up to this diagram right here. Okay, I didn't actually draw out the triangles to avoid clutter in the diagram, but if you just follow my cursor there like that, that triangle is similar to this triangle. And this triangle is the 5, 3, and 4. And so the angles here are the same as the angles there. And so we know that this angle right in here, we already got that. That was that 53.1. Okay, so this angle in here is 53.1. This angle in here is the 36.9. Okay. That means that this angle here is 36.9. You say, well, how did you get that? See that FW? It's parallel to FGW. Okay, so because these two are parallel to one another, and the ladder cuts between these two parallel lines, that says that that angle in there must equal that angle there. Okay, and that's one of Euclid's postulates. I forget which one, but basically, if you have two parallel lines and then you got another line that cuts them, then the angles, the inner angles, there and they're going to be the same. Okay, and we have those numbers. Okay, so this one's 53.1 and that one was 36.9. Okay, so we can make use of that. All right, so yeah, no way to avoid that geometry for these ladder problems. Okay, so let's go through it. All right, well, first, the torque at the ground, whether the y or the x component is 0, because the axis of rotation is right there. That means that r is 0 for those two forces, and that means that the torques are 0. Okay, so great. Okay, those forces act right at the axis. Okay, so we've seen that already. Now, what about the torque due to the force of gravity on the bar? So that's going to be r of sine theta. How far is it from the axis to where the force of gravity acts? And let's look at this diagram here again. So there's the axis right there. The whole ladder is 5 meters long. Half of that is 2.5 meters. So there's your r, 2.5 meters. Okay, whoops, there we go. So there's the r is 2.5 meters. What about F? Well, F is 200 newtons, the weight of the weight of the bar. Sorry, the weight of the ladder. Okay, and what about theta? Well, for theta, that's why we did this. This is like the ladder, and there's the force of gravity going straight down. And so what's that angle between the ladder and gravity down? 53.1. Okay, and so over here, for this angle, oops, I scrolled too far. That angle there is 53.1. And 2.5 times 200 multiplied by the sine of 53.1 is 400 Newton meters. That one is going to be clockwise. Excuse me. That one's going to be clockwise. Okay, and you say, why clockwise? Well, if you take a look here, again, just turn off all the forces. This is the only force acting, and it's allowed to pivot around that point. If I pull down like this whole thing is going to start turning like that around that axis, and that is clockwise. Conversely, that one has to be counterclockwise. Okay, so because they two have to, the two torques have to cancel. All right, so great, we've got 400 Newton meters clockwise. What about the other one? Well, the other one is 5 meters from the axis to where it acts. Okay, scroll back. I think it's pretty obvious, but just in case, there is the axis there. Where's that force acting? Way at the other end of the ladder. How long is the ladder? 5 meters. Okay, so r is 5 meters for that. All right, so here we have r is 5 meters. F, it's the force of the wall, and we don't know. Okay, we don't know how big it is, so just leave the symbol there. And the angle, that angle is 36.9. Why? Well, I just explained that. That's because the ground makes here, let's go back to this diagram here. The ground makes a 36.9 degree angle with the ladder, and that means that the normal up here is also going to be at 36.9 degrees to the ladder, because those two are parallel to one another. They're like this. FW is parallel to FGX, and if this angle here is 36.9, then that is also 36.9, okay, by Euclidean geometry. All right, so we've got that angle there, 36.9, and if we do 5 meters times sine of 36.9, we get 3, okay, and that 3 is not a coincidence. If you go back to the whole triangle, this is all a triangle. Hypotenuse is 5. Okay, one of the sides is 3. Okay, the height of the ladder along the wall above the ground is 3, and that's where that's coming from. That's why you're getting exactly 3 there. Okay, and that one's counterclockwise. Now the clockwise torques have to balance the counterclockwise torques. So 400 Newton meters has to balance this 3 meters times FW. Here it is. Okay. And so now we just divide both sides by 3 meters, and we're going to get that FW is 133 newtons. All right, so now if we substitute that into equation 2, which is the one that balanced the x components, we find now that the ground must also be pushing back in the other direction with 133 newtons. Okay, so we could go back to the free body diagram at this point and draw in all the numbers, or put in the numbers, not redraw the diagram, but just put in the numbers. We had this to start with. That was 200 newtons down, and it had to be balanced with 200 newtons up. So you can see the down force here, 200 newtons, is balanced with the up force of 200 newtons. Okay, the force to the right here of 133 newtons is balanced with the force of 103 newtons to the left. Okay, and do the torques work out? Well, that's a little harder to see because of these funny angles, but yeah, they do. And we put the axis there, but you could try if you like putting the axis there or putting the axis there, and it would still work. Okay, it would still just work out just fine. All right, so there you go. There's the that solves it. But just to finish this off, I thought, you know what, let's find the magnitude and direction of the force of the ground. You'll be surprised. It's not exactly along the ladder. It's actually at some angle. So what is the magnitude of FG? And what is the direction? Okay, and so for the magnitude, just use Pythagorean Theorem. It's the square root of the x component squared plus the y component squared. The x component was 133, the y component was 200, and that gives you 240 newtons. So the ground is pushing with 240 newtons. Okay, so if you take a look up here at the diagram, it's pushing up with 200 newtons. It's pushing to the right 133 newtons, but those two combined together are 240 newtons of force. And the angle is going to be inverse tangent of the y component divided the x component. Y component was 200, x was 133, and so that gives you that the angle is 56.4. Okay, which is kind of interesting because the angle the ladder makes with the ground is 36.9 degrees, but the force is actually at a different angle. It's at 56.4 degrees. Okay, so there you go. That's the last problem, and that's by far the hardest problem of the set. Okay, and what made it difficult is that you had to identify some angles. Okay, so you could see if you go through my problems, they progress in difficulty. In the second problem with the bar and the sine, what was easy there is that you could resolve everything into angles which were 90 degrees, or either 0, 90, or 180 degrees. In this one, it's not so easy. There's really no way to avoid here when you're looking at this diagram that you need that angle in there, okay? Because when you do the R vector there, you're traveling along the ladder and you make a turn and it's not a 90-degree turn, okay? It's not a 90-degree turn. And you do the same thing up here and you make a turn and that's, again, not a 90-degree turn. And so you need that angle in there. Okay, that was that 53.1, and you need that angle in there, the 36.9. Okay, and you say, how do I get those angles? Well, the only way to do it is by this kind of a similar triangle analysis right here. Okay, all right, guys, that's the end of this lecture. Thank you.